we're going to derive what's called the convolution integral. This is important, and it's a core concept in signal processing, digital signal processing, communications theory, and many other parts of engineering. So first, a little bit of an introduction, and then we will go on and derive the formula for this important operation. And then in the next video, we'll do a more detailed example with specific signals. The core concept behind the convolution operation is that you can take two things. You can take an input x of t, and given a linear time invariant system that has an impulse response h of t, so we have, when you say h of t exists, you assume that the system is linear and time invariant. Those two facts taken together are going to allow us to derive an operation called convolution, which will let us derive the output. Now, we can do this for any signal x of t. Once we have this operation, it's going to be a recipe, it's going to be a list of steps, it's going to be a method that you can apply given just those two things on the left. H of t, the impulse response, which we saw how to derive in the last couple of lectures, and then any given arbitrary input signal. Why do we want to do this, and how do we use this formula? There are three key reasons. The first one, and we're going to do an example of this in the next video, is called analytic convolution. This is going to be our most basic and first approach using convolution. We're going to follow the formula literally, and we're going to be able to determine what the output y of t is. And we'll do, like I said, we'll do an example of that in the next video. Then we're going to look at a method called graphical convolution. Graphical convolution is going to allow us to use our intuition about causality and certain constraints on inputs and outputs of systems to look at the convolution formula that we derive and interpret it more logically. So number one, we understand what's happening with the operation, and number two, we can make some large simplifications. And then third is something called numerical convolution. This approach to convolution can be done on a digital computer for sampled signals, and this is what you're going to be doing quite a bit when you get into digital signal processing EE3032 next quarter. The next example video is going to cover parts 2 and 3, is going to cover parts 1 and a little bit of 3, and then graphical convolution is actually covered in the next section of the book in section 2.4. So we're going to be spending quite a bit of time on convolution because it is so important. We're going to take 5 steps to derive the formula for convolution. Each of these steps makes use of something we already know or we've already proven about linear time invariant systems. In the first step, what we do is we say in a linear time invariant system, we're going to let the input be the impulse function, and that enters the LTI system. And out of the system, what do we know about the output? We know it is that signal we derived earlier in chapter 2 called h of t, the impulse response. Now we're going to apply some other properties. First thing we're going to do is we're going to delay this input by tau seconds. Now, since the system is linear and time invariant, when we do that delay, we know that the output y of t is the original output h of t, but it's also delayed by tau seconds. So everything we're doing here directly follows from the fact that the system is linear and time invariant. So if the system has those properties, that's what enabled us to calculate h of t, the one impulse response for the system in the first place. And those properties are also what allow us to go through the steps of this derivation. And at step 5, we're going to get one of the most important formulas in all of signal processing. Next step we're going to do is we're just going to apply the scaling property. We are going to scale the input signal. Instead of being a impulse with area 1, we're going to scale it by a function x, and we're going to have it be of the independent variable tau here. So at the time the impulse occurs, which is at time tau, which is what we have from step 2, that's the only place where the value of x would matter. So let's just multiply it by a constant value x. So everything else is going to be the same. The system is linear. Since the system is linear, one of the properties it has is the scaling property. So since we scaled the input by the constant number x of tau, we know the output will also be scaled by x of tau. The next operation that we're going to do is we are going to integrate over the variable tau. So on the left-hand side, we'll integrate over the variable tau, and the variable tau will disappear. And on the right-hand side, we're going to do the same, and we'll have an integral expression on both sides. Now, let's write it out, and then let's talk a little bit more about what this means physically when we do this integral. So on the left-hand side, I'm doing an integral over all values of tau, and I'm integrating this expression here. And related to the concept of superposition, which we have for linear systems, if I integrate or add up the area from all those items on the left-hand side, because the system is linear, I've accumulated the same items on the output. So I can apply the same operation to get the output y of t. I can do the same integral of the expression here Now in step 5, we're actually going to show why this is useful. The really cool simplification happens on the left-hand side here in step 5. Let's look what's happening to the input to this system. We need to go back to the sampling property, and we can make a really powerful simplification of what is on the left-hand side. Notice here we do an integral over the single variable tau, and in the expression is this impulse response. This impulse is 0 almost everywhere. The only place it's not 0, causing the whole integrand to be 0, the only place it's not 0 is when this argument right here is itself equal to 0. So when t minus tau equals 0, or when t equals tau, then something interesting happens, and we apply the sampling theorem. And the sampling theorem, we went through a few steps, and the conclusion of the sampling theorem was when you have this expression, the answer is x of t. Now, what we did in the sampling theorem was we showed that first step is this x of tau. It doesn't matter what it is for most values tau. It only matters what it is when t equals tau. So the first step was we replaced this tau with t, and we had x of t here. But now we're integrating with respect to tau, so x of t could come out of the integration, and all we were left with was find the area under the impulse, integrate the impulse with area 1, and this x of t was left over. And y of t does not change at all. This is y of t here. I'm just going to rewrite it because it's such an important expression. This integral tells us now how for any input x, we can find the output y if we know the impulse response h, just by following this integral. And in the next video, we are going to do an example, and your book also has in section 2.3 two large examples, and there's other examples throughout of applying this integral.